Hello, in this video I would like to present my group's work for the group project. My group includes Dylan Don, Taja G, I'm sorry, I wish I could pronounce your last name, and myself, Tristan Gonzalez. We've all worked through this problem together, and that is how we were able to piece together this presentation. I will be doing the narration for our scenario. For this project, we were to ultimately model the administration of propofol on an unnamed patient. On this first slide, we are covering the problem statement with the background information on this particular drug being used, as well as how this drug is being used in this scenario on the patient. Additionally, with the question to answer is the dosage information. Propofol, also known as Diprivan, is an anesthetic used during general surgery. The recommended dosing is 0.15 milligrams per 1 kilogram of weight per minute. The body is able to process and reduce the amount of propofol in the bloodstream by 6.9% per hour. Suppose a 175-pound person goes into outpatient surgery. The surgery lasts about 100 minutes. Anesthesia will begin 10 minutes prior to surgery to get the patient under, and it be administered throughout the entirety of surgery. When surgery ends, infusion of propofol will cease, and the patient will go into recovery. The patient will be then discharged once the anesthetic is 93% metabolized in his bloodstream. We can then see that the question to answer is, without consideration of wait times and other hang-ups, how long will the hospital have the patient for? As we move to our next slide, we'll be getting into the development of the propofol model and everything to consider in this scenario. Now, in order to get the solution process going, we need to first distinguish the differential equation or equations that we can. As it so happens, this scenario involves two parts to the differential equation, one being the administration of the drug, which is considered to be the rate in the system, and that of the ability that the patient's body has in processing this drug. Since the administration is adding to the system, or rather the patient's body, we can consider how their body breaks down the drug as a negative factor to this equation. We are given the weight of the patient in pounds, but we have to convert that weight into kilograms in order to find the correct dosage. We can see that the conversion below being approximately 79 kilograms, we then want the dosage per hour for that 79 kilograms patient, and so we end up with 714.42 milligrams per hour. So we have that amount entering the system and have the numerical value of 6.9% leaving the system. Now remember, we have to identify the variables and define them for this situation. We can see that the y variable is the milligrams of the drug, while the variable t is representation of time in hours since the patient is administered the drug, and so we are left with the converted equation 714.42 minus 0.069y. Now that we know what differential equation we're solving for, we can then set up the general solution for this differential equation. For the general solution, we use separation of variables to find the general equation with variable k to solve for using the initial condition. Since the patient has not yet received the drug, we can say that initially the patient has 0 milligrams starting off, and using those values we can then see that the value of k is 714.56, this giving the following particular solution. Now, it is important that we understand that this is the particular solution to find the dosage of the drug in milligrams for the 10 minutes prior to the surgery as well as the 100 minutes during the surgery. Reading into this next slide, to the right, we can see that the slope of the field of the original differential equation, which is used to find the amount of propofol, is in the patient when administration is stopped. For this particular slope field, we utilized a given program that graphs the differential equation as well as reveals how it behaves starting at multiple initial conditions. We can see that each of these initial conditions will approach a value that appears to be approximately 10,000. This next slide is to show the specific use of the separation of variables that has been covered in a previous slide, but this time is easier to read and understand. Moving on, we can see the equilibrium and phase line analysis. Essentially, phase lines are used in differential equations to find the equilibrium points and are analyzed to see the behavior of the solution. The field will point either wholly towards or away from the solution depending on the scenario. As seen below, both of the phase lines created from the equilibrium points of the scenario can be described as sinks, also known as attractors, that are bistable. As seen below, and as previously mentioned, the solutions to the differential equation is just over 10,000, but now we know the approximate value to be 10,354. To the right is the analysis for the second differential equation to be used in this scenario, which depicts the behavior of the system after administration has ceased, and, as can be guessed, the differential equation will eventually make its way to the equilibrium value of 0. Now in this next slide, it shows us the behavior of the now solved differential equations, the first being that of the administration prior to and during the surgery, and that second drop seen is when the administration has ceased and the patient is now processing the drug out of their system. Now, to be taken note of, we can see that the time when the drug is nearly out of the system is just before 100 hours, which will be shown to be true in the slides following. To the right can be seen the values found when using Euler's method to determine how much propofol is 7% of the drug administration. Essentially, this tells us the approximate value of the drug that we are looking for when 93% has been processed. Now, with everything found using the slope field, phase lines, and Euler's method, we can know for sure the dosage in milligrams when the administration is stopped. Relating these together, we have the following on screen. All of the above have displayed equilibrium within the scenario. The phase lines show that the equilibrium points of the autonomous ODE created by the scenario are in fact represented within the slope field. The slope field approaches the same equilibrium value that the phase line method had defined, 10,353.91. No matter the initial condition, the slopes will approach that same value at a decreasing rate. Now, for the solution to the differential equations, that value is where the administration of propofol is ceased, and the only effect in the system is the decomposition at a rate of 6.9%. As seen in the model, the infusion is stopped when y of t equals 10,353.91, represented by the equilibrium values of both the phase lines and the slope field. With that all being said, we have yet to find the solution to the problem statement, that being, how long will the hospital keep this patient? On this final page, we see the process of Laplace transforms to find the time in minutes. After finding the equation to get that time, we have the ability to plug in the value of how many milligrams of the drug are in the system when administration is stopped. By doing so, we can then multiply that by the numerical equivalence of 7% to find the answer to the question statement. We then add that value to the time of the surgery and find that the patient is within the hospital for approximately 2,422 minutes. Thank you.